Guys, in this video, we'll talk about this thing called prime factors. Prime factors are the things that the technologist, whoever's taking the X-ray, has to take into consideration whenever he or she is taking an X-ray. It's the things that they manipulate, they change, that they work with on a daily basis to get the kind of X-ray and the quality X-ray that they want to get. So we need to look at what they're doing and understand the relationship between those. First of all, what factors are they going to manipulate in there? What are they going to change? What are they working with? One is called milliamp seconds. It's a measurement of the amount of tube current and the number of electrons crossing through that tube. And if you recall, we're talking about the amount of electrons that are generated by the cathode inside the X-ray tube. And the milliamp seconds also is a function of time. So how long do we generate those electrons that are flowing through the tube? And those things are used together. So that's why it's called milliamp seconds. The other one is the kVp or kilovolt peak that they can actually adjust, which has to do with the quality of the X-ray beam and increases the speed and the energy of those. So as we turn that high voltage up, that kVp up, we impact the anode of the X-ray tube with more energy from those electrons. And then distance, basically how far away is the X-ray tube or the source of the X-ray away from our target or our patient. And we see here that intensity varies greatly with distance, and in fact, it varies at a rate of the square. So as we move two times away from the source, we actually end up reducing the X-ray intensity by a factor of 4. So keep that in mind as we talk about prime factors as well. And then this other term we need to be familiar with, SID, source to imaging distance, how far from the source the subject is actually placed. Okay, if you know anything about electronics, you know that I in electronics terms stands for current flow, right? But this is not, we're not talking about electronics now. We're talking about X-ray energy and the intensity of the X-ray beam in particular. So when you see I in these formulas, I stands for intensity, and specifically it means intensity of the X-ray beam. And we see here a relation, I intensity 1 over I intensity 2 is equal to the milliamp seconds 1 divided or over the milliamp seconds 2. So we can see that what we're actually going to end up doing is some math here to figure out, you know, if we change one, what's going to be the change on the other side. We're going to talk about some examples of what the technologists are going to do to change the intensity or the quality of the X-ray beam. And we're going to start with one of them here. Is sets a certain technique calls for 100 kVp at 25 milliamp seconds. It results in an X-ray intensity of 28 millirems at the patient. And then it asks the question, if the MAS is increased to 35, what will the intensity be? Well, before we determine what the actual intensity will be, you need to ask yourself a question. What do you think is going to happen? We're increasing the milliamp seconds, the MAS, from 25 to 35. It stands to reason then that the intensity would increase as well. So if it's going to increase, we would expect to see something greater than 28 as a result. But what we're going to do is actually end up cross multiplying. So let's take a look at that. In our example here, we see the I1, intensity 1, was 28 millirems. MAS1 was 25, MAS2 is 35. So we're going to cross multiply 28 times 35 and divide by 25. Just showing that in a little bit more detail here. And then we end up with our result of 39.2 as our second intensity. So as we increase, if you remember what we did, we increased the MAS from 25 to 35. We expected to see an increase in intensity, and in fact we did. We see the intensity increase from 28 to 35. This example 2 here is showing the same kind of problem we just worked. We're talking about a change in intensity based on a change in MAS. And you'll notice in both of these examples, it tells you what the KVP is. And really that's a little bit misleading because you don't need to know what the KVP is in this particular example to determine what the change is going to be. It's just thrown in there to confuse you or to misdirect you. A certain technique, again, calls for 75 kVp, 60 MAS. It results in an intensity of 12 millirems at the patient. If we decrease the MAS to 25, what would the intensity be? Okay, one of the first things you need to do is ask yourself the same question. What do we expect to see happen? If we're reducing the MAS, and we're not doing anything, especially with the KVP, but reducing the MAS, what do we expect the intensity to do? Well, we would expect to see it drop. Here again, we're plugging in our numbers. Intensity 1 was 12 millirems. The MAS1 was 60. We reduced it to 25. We plug our numbers in here, we'll cross multiply, and we come up with 5 millirems. So our intensity did decrease just as we predicted that it would. Okay, now we're going to use the KVP information that we see. We're actually going to manipulate different prime factors now based on the KVP. We're going to substitute the KVP in our equations. So now what we see is rather than having the MAS given to us, we're given the KVP and we're asked the same question. We're going to manipulate our KVP to come up with changes in intensity or vice versa. The difference is even though it appears to be still directly proportional, we see that we're actually having to square the KVP to get our answer. So keep that in mind. Okay, our first exercise, manipulating KVP, says that if a certain technique calls for 75 KVP, 50 MAS, and results in an intensity of 20 millirems at the patient, or if the KVP is increased to 125, what will the intensity be? Well, first of all, in this case, we don't need our MAS number. All we need is our KVP and our intensity numbers here. And it's asking, if we started out with 75 KVP and we increase it to 125, what would the intensity be? Well, common sense will tell you that the intensity is going to go up. So just sort of keep that inside, the back of your mind once you check your answer to know whether it's right or not. In the previous example, it gave us a KVP1 of 75, KVP2 of 125, and an intensity 1 of 20. And if you do the cross multiplication, I'll let you work it for yourself. Basically, you multiply 20 times 125 and divide by 75. And that should give you an increased intensity as a result of an increase in the KVP. Here we see a second exercise where a certain technique calls for 100 KVP, 50 MAS, an intensity of 40 millirems. And then it says if the intensity is decreased, what will the new KVP be? Well, again, we don't need this 50 MAS, so forget about that for right now. We're going to decrease the intensity from 40 to 22. We would expect that will require a lower than 150 KVP. So I'll let you work through that one to see what the results would be. The last exercises we're going to work on here have to do with distance. As we change the distance of the patient from the X-ray source, we see a dramatic change in the intensity. And the note here says that the distance, and this should say X-ray, exposure are an inverse square law. So as we move away from the X-ray beam, we greatly reduce the intensity. First example in the distance has to do with an exposure, a KVP of 95 with 20 milliamp seconds and a source to image distance, SID, of 150. And again, SID just means how far the patient is from the source of the X-ray energy. The exposure at the image receptor is 50 millirems. If the same technique is used with a SID of 100, in other words, we're getting it closer, what will the exposure be? Well, you should know that if we're reducing the distance as we are here, then the X-ray exposure or the intensity of the beam will actually increase. And here we see our numbers plugged into the formula. We see now that our initial, we're inverting this, by the way. This is I1 over I2. This is SID 2 over SID1. But we're going to plug these numbers in, and 15 times 150 divided by 100 will result in an intensity 2 of 33.75. So we can see that relation.